Good morning, everyone. This is the Lattice-based Cryptography I session. We have two talks for you, one presented here live and one online. The first talk is about complexity of Wagner's algorithm by Leo, Lynn, and Johanna. And Lynn will give the talk here.
Thanks for the introduction. Hi, everyone. I'm excited to share this joint work with Leo Duca and Rishab Goyal on an algorithm that runs in sub-exponential time for the short integer solution problem. Our work is motivated by an algorithm for one of the most prominent computational problems in post-quantum cryptography, namely the learning with errors problem. And learning with errors, or LWE, asks to solve a noisy system of m linear equations in n variables modulo q, where noisy means that each equation is perturbed by some random error from some known distribution. And this error seems to make this problem rather difficult in some settings. And the hardness of LWE depends on those parameters n, m, and q, where m and q are typically implicit functions in terms of n. Now, the more LWE equations you have, the larger m, the problem can only get easier. So it's interesting to understand at what value of m this problem is no longer hard. And in 2015, Kirshner and Fook presented an algorithm for learning with errors with narrow error distribution, meaning that the error support is only a very small subset of the integers mod q. And they claim that this algorithm runs in sub-exponential time for parameters where m is essentially linear in n, the number of variables. Yet a few years later, Harold, Kirshner, and May found an error in the proof that they could only resolve by considering parameters with m of order n log n. Yet it remains a common belief that it can also be solved or fixed for m of order n. The question is how. And in our work, we make progress by showing this for the first step of Kirshner and Fook's algorithm. This first step of Kirshner and Fook's algorithm solves an instance of the short integer solution problem, SIS. And this instance is derived from those m LWE equations. The short integer solution problem is defined for different norms, and in this talk, I'll mainly consider the infinity norm. And in that case, it's defined as follows. Consider parameters n, m, q, and some norm-bound beta. Then an instance is given by a matrix A sampled uniformly at random from all the n by m matrices with integer entries defined modulo q. And the problem asks to find a non-zero integer solution to the equation ax is 0 mod q that has infinity norm bounded by this norm-bound beta. Now, depending on beta, this problem can become intractable, namely if beta is too small, or trivial if beta is too large. But it's widely believed that there is a regime of parameters where SIS infinity is hard, and in particular, SIS infinity underlies the security of the NIST standard MLDSA, also known as dilithium. And in our work, we reinterpret this Kirshner-Fook SIS step as going through a chain of projected lattices. And this lattice perspective then allows us to show that there exists a sub-exponential time algorithm for SIS infinity for parameters where m is now only required to be slightly larger than n, as opposed to n log n, and for non-trivial norm bounds such as q over poly log n. This is an asymptotic result, so it does not affect the concrete security of MLDSA, and we actually give some explanation in our paper. And moreover, this asymptotic sub-exponential time complexity does also apply to other variants of SIS in the L2 norm, namely to non-trivial instances of the inhomogeneous SIS problem and SIS star. And whereas our work was motivated by LWE, we actually do not yet obtain a direct corollary for some technical reasons, but we have some ideas to make this work, and hopefully this can be resolved soon in the future. So let's go look at this algorithm for SIS. Kirshner and Fook's SIS step is actually a refined version of Wagner's algorithm for the generalized birthday problem. And to see how this algorithm can be used to solve SIS, consider an instance given by a matrix A. Now, assuming that this matrix is of full rank, we can write it in systematic form, meaning that A is the concatenation of a matrix A prime and the n by n identity matrix. Solutions can then be determined by the first m minus n coordinates, because the remaining n coordinates are modulo q defined by this matrix A prime. And this then motivates the following strategy. Start by sampling many short vectors of integer coefficients in dimension m minus n. And those vector sets will then lift to a solution to Ax is 0 mod q. But this lifted vector need not be small because the extra n coordinates can still be rather large in infinity norm. However, what we can do is we can iteratively combine such vectors to eventually end up with short solutions to Ax is 0 mod q, where short is holds now for all m coordinates. And this combination step is done in a style of Wagner's algorithm by considering one block of coordinates at a time. So specifically, consider parameters b1 up to br that sum up to n, the number of rows of the matrix A. Now remember that A was the concatenation of A prime with the n by n identity matrix. And this bi now define a sequence of matrices A1 up to AR that are also the concatenation of some matrix AI prime and an identity matrix, where AI prime consists of the first B1 up to BI rows of A prime. And the algorithm will then iteratively construct short solutions to AIX is 0 mod q from short solutions to AI minus 1x is 0 mod q. Kirsten and Fuchs' algorithm can then be presented at a high level as follows. It's defined for parameters capital N, R, P1 up to PR, and B1 up to BR that will be optimized to achieve the desired runtime complexity, or the optimal runtime complexity. And the algorithm will start by filling a list L0 with capital N random vectors over the instances in dimension n minus n. And specifically, the entries will only be -1, 0, or 1. And this means that these vectors will then have infinity norm bounded by 1. Now then, in iteration I, ranging from 1 up to r, the algorithm will lift vectors in our current list, Li minus 1, to solutions to the equation defined by Ai. And those additional bi coordinates are represented here by a vector y, will not necessarily have short or bounded infinity norm, but similar as I said before, those lifted vectors will be combined to end up with a list Li of short solutions to the equation defined by Ai. And this is done by searching for lifted vectors such that their additional bi coordinates represented by y1 and y2 are such that their difference is bounded in infinity norm by q over pi. Remember that pi was one of those parameters. And this is actually done using a notion of lazy modulus switching, but it achieves a norm bound like this. And in fact, the pi will be chosen decreasing in I, and that ensures that in later iterations, this norm condition is actually less tight. And whereas I refer to the full paper or to Kirsten and Fuchs' paper for more details, this then allows to take the bi increasing in I, and this is key to the sub-exponential complexity. Now, we already knew that x1 and x2 had bounded infinity norm. We now also know that y1 minus y2 is bounded in infinity norm. So taking the difference of those two lifted vectors, we'll end up with a short solution to the equation defined by Ai, and we add it to our list Li. We repeat this for r times and output the final list. And then for some parameter regimes of SIS, we can show that there exists a choice of algorithm parameters such that this algorithm runs in sub-exponential time. And the output list consists of solutions to the equation defined by A. Also, I should maybe have said AR is equal to A, such that their infinity norm is bounded by beta. However, to be an SIS solution, we do not only want a short solution to Ax is 0 mod q, we also want one that is non-zero. And this is a crucial issue in the original claim of Kirchner and Vogt that seems hard to resolve because it's hard to keep track of the distributions of the vectors after the first iteration. And the way we resolve this is by switching the perspective of the algorithm. This SIS algorithm can actually be viewed as walking through a chain of lattices lambda 0 up to lambda r. Specifically, it starts with sampling many short random vectors in the integer lattice of dimension m-n, which I'll call lambda 0. And then in iteration I is 1 up to r, it lifts and combines short vectors in the current lattice, lambda I minus 1, to obtain short vectors in the next lattice, lambda I, that is defined as the set of all integer solutions to the equation defined by AI. And in the end, it will output a list of short vectors in the final lattice lambda r, which is the set of all integer solutions to AX is 0 mod Q. Now, this latter lattice is also known as the SAS lattice or the kernel lattice of the matrix A, often denoted by this symbol in gray. And note that indeed, solving SAS is equivalent to finding a short non-zero vector in this SAS lattice. We also reinterpret the lifting and combining step. So remember that we can lift vectors in lambda I minus 1 to vectors in lambda I. And this is another way of saying that lambda I minus 1 is a projection of lambda I. And then vectors, those lifted vectors in lambda I were combined if they satisfied some condition that was related to this parameter pi. Now we can actually also reinterpret this in a different way. Namely, vectors in lambda I minus 1 are lifted to vectors in a superlattice of lambda I, namely lambda I prime, that is defined by this parameter pi. And specifically, lambda I minus 1 is a projection of lambda I prime, orthogonal to the span of the integer lattice of dimension bi scaled by a factor q over pi. Now, I don't expect you to immediately understand this definition and why this is the case. But what I would like you to take away is that now the combination step can be interpreted in terms of cosets. So lifted vectors will now be combined only if they belong to the same coset modulo lambda I, meaning that taking the difference will end up with a vector in the lattice we wanted, lambda I. And visually this looks as follows. We start with the lattice lambda 0, so we go from right to left, and we walk through these lattices lambda 1 up to lambda r, the SIS lattice, while zigzagging through these auxiliary superlattices by lifting and combining. Now recall that the issue was to show that the output list contains a short non-zero vector in the SIS lattice. And that this was hard because it was hard to keep track of the distributions of the vectors throughout the algorithm. Now, this switch of perspective does, of course, not immediately solve the issue. It's still the same algorithm after all. But what it does do is it opens the door to other lattice techniques, in particular, the discrete Gaussian distribution. The discrete Gaussian distribution has some very nice properties that make it very useful in controlling the behavior of discrete Gaussian samples during algorithmic operations. So what we do is we fill the initial list, L0, with discrete Gaussian samples over the integer lattice in dimension m-n, this lattice lambda 0. And this then, using some slight modifications of the lifting and combining step, allows us to control the distributions of the vectors in the list Li. And here we rely on a lot of existing results regarding the discrete Gaussian distribution to show that indeed lifting to the superlattices and combining vectors in the same coset will still end up with something close to a discrete Gaussian sample over the next lattice lambda I. And under certain conditions related to the smoothing parameters of the lattices that we encounter, we can then show that the vectors in the final list are similar in some precise mathematical sense to discrete Gaussian samples over the SIS lattice. And this is another way of saying that this algorithm has become a Wagner-style Gaussian sampler. And Wagner-style because remember that we were considering blocks of coordinates or blocks of dimensions at a time. And I should maybe also mention that it's not always easy to sample from a discrete Gaussian distribution over a lattice. For the integers, so in this first step, that is something we know how to do. But for arbitrary lattices, it's typically much harder. Now, and then it can be shown that with high probability, a vector in the final list is short in L2 norm, but also in L infinity norm. And most importantly, it is non-zero. So to conclude, we reinterpret this Wagner-Stell algorithm for SIS in terms of lattices. And using discrete Gaussian tools, we can then show that the output list does not contain too many zeros in the end, or at least it contains one non-zero short element. And this Wagner-Stell Gaussian sampler solves non-trivial instances of SIS infinity in homogeneous SIS and SIS star in sub-exponential time, including for parameters where m is only slightly larger than n, as opposed to requiring it to be at least n log n. And as I already mentioned, this is an asymptotic result, so MLDSA is not broken. And I would like to end with two future directions. So first, I would like to say this Wagner-Stell Gaussian sampler is presented for SIS lattices, but actually is not at all restricted to such lattices and could also work with other chains of lattices. So it would be interesting to figure out if there are other applications of this sampler. And finally, it would be great to finally resolve the question that I started with at the beginning, whether there is indeed an algorithm for narrow error LDB with a reduced number of samples. That was all I wanted to say. Thank you very much.
Thank you so much. Are there any questions? If so, please come to the mic.
So your technique shows the existence of some non-zero solution. Can you use similar techniques to show that there are many of them? Because using this toolbox from discrete Gaussian distribution, I believe that you could give some lower bound on the number of non-zero solutions, couldn't you?
Probably. Possibly. I'm not 100% sure. I think you can show that there exists a certain number, but this depends on how close we get. So as I said in the previous slide, we get something that sort of closely behaved as discrete Gaussian samples, and it's really important, like how close you get to be able to show that many samples have such and such property, and that's actually what's the difficulty in going also to LWE. But there are some ways. So if you can get it close. If you can improve this closeness, then you can show that the need for more output vectors, because this algorithm will output a lot, like sub-exponentially many solutions to SIS, but showing that all these solutions are in fact short and non-zero.
Okay, another short question. You mentioned that your techniques work for L2 and for L infinity. Does it work for other norms?
Yeah, so we rely here on a lemma by Banashik,
yes,
if I pronounce it correctly, which I know exists for L2 and L infinity norm. I wouldn't be surprised it exists for other norms as well, yeah.
So that lemma is not known to be true for L1?
I don't know.
Okay, thanks.
So yeah, thanks for the question.
Thanks, Adi. Are there any other questions? If not, then let's thank the speaker again. The next talk will be an online talk on refined attacks on LWE with hints by Yin Zheng, Hadong, and Qing Feng. And Ying Zheng will present the video.
Hello everyone. Today we give a presentation on our work, a new analysis of solving the LWE problems with side channel information and form of hints. We will first introduce some background knowledge about LWE, hints, and existing approaches to LWE with hints. Then we will introduce our main work, a new framework that translates side-channel hints about LWE into an independent problem on lattices, which leads to a new method of integrating hints with the original LWE lattice. We begin with the learning with error problem, or LWE. The problem has been playing a central role in the development of post-quantum cryptography. Given matrix A and vector B as public keys, LWE requires recovering the secret vector S, where S and error vector E have small entries. Generally, the LWE problem can be reduced to a shortest vector problem, or SVP instance, by constructing this form of lattice. It can be verified that the lattice vector composed of secret S and error E is significantly short vector in the lattice. Therefore, the problem can be solved by finding the shortest vector in the lattice. This strategy is usually called primal attack and is adopted as a mainstream approach. However, real-world security problems may stem from other issues such as side-channel attacks. Analyzing LWE's resilience to side-channel attack is therefore one of the key questions raised in the standardization and development of lattice-based post-quantum cryptography. In this work, we adopt the idea that formulates different kinds of side-channel leakage and hints. In other words, equations about the secret vector. Considering practical background, we focus on the following types of hints. First, the perfect hints or equations of integers. Second, the modular hints or equations of modular rings. And third, the mod Q hints or special kind of modular hints whose modulus is same as the LW instance, that is Q. Fourth, the approximate hints, that is erroneous equations about the secret vector. At the early stage, researchers used ad hoc methods to analyze specific cryptographies, and they usually require a large amount of leakage. The first systematic framework to quantify LWE's information was offered by Degman Sode and others called the DDGR framework. The basic idea of this framework is successively integrating hints into the primal attack lattice. For each hint, the framework computes dual bases twice, which may be slow when many hints are involved. Then, May and Novakovsky improved the framework by designing a more efficient lattice construction method called the MN framework. In practice, they proposed a linear algebra approach for mod Q hints. Given k hints, it reduces the dimension of LWE from n to n minus k. However, this efficient method is not applicable to perfect hints and modular hints. In these cases, the MN method uses a L3-based approach, which is significantly slower. Another key contribution of this method is discovering the too many hints regime, where enough hints are provided to make solving LWE efficient in practice. While DDGR and MN already provide impressive frameworks of integrating LWE with hints, they still leave us with interesting problems to explore. On the one hand, the pioneer work of DDGR gives a theoretical proof about hint integration, but it can only process one hint at a time. On the other hand, the MN method is faster when integrating numerous hints, but we're still interested in a generic framework for all the hints combined. Moreover, we want to find a clearer proof of correctness that does not rely on additional assumptions. We now introduce the main contribution of our work. We introduce a novel framework to extract information from the hints themselves before integrating hints with LWE. From hint-centric view, we transform the hints to a special variant of small integer solution problem, or SIS, whose secret vector is identical to the corresponding LWE. Therefore, our framework decouples hints from the LWE problem by building this SIS instance before including LWE samples. This simplifies and clarifies how hints provide additional information and helps us solve LWE, and provides a new perspective on the special case of too many hints. To illustrate our method, we describe the transformation of perfect hints as an example. Recall that perfect hints essentially give equations in the form as displayed here. In MN method, the literature is unable to process perfect hints with their smart methodology with molecule hints, but there is no guarantee that a random matrix is invertible over integers. To deal with the shortcomings of previous results, we start from a lattice constructed only from hints. This means that we interpret hints as equations which independently provide information about the secret vector. To initiate our framework, we formally define a lattice problem as here. We call it the SIS problem, which is a variant of SIS. Obviously, the problem is derived from the common SIS, except that we define it over integers instead of modular rings. From here, we introduce how to construct this lattice that solves the SIS instance. The lattice basis is defined as H matrix here. Note that append this identical submatrix block to keep the coefficients of matrix transformation. Therefore, we can verify that the last coefficient of the secret vector key is a short vector in the lattice. In other words, the practical secret exists in a sublattice where vectors have zero prefix. So the next question is how to get the basis of this sublattice. We propose that the sublattice basis can be extracted from the matrix H. We focus on the block on the upper left, which is composed by hint vectors. By Gaussian elimination, we can apply row transform that reduce this block to its row echelon form. This block has n non-zero rows and k columns. Then we still have n minus k rows, 0 rows at the bottom. And we can use the upper k rows to reduce this last row to 0. This is ensured by the hint equation. In the end, we reduce this ZSIS matrix to this form that only has k non-zero rows in the upper left block. Since we are looking for a sublattice vector that have 0 prefix, we can just remove the non-zero rows and keep the last n minus k plus 1 rows for our later transformation. In conclusion, run Gaussian elimination on the upper left block of H and reduce the last row. Finally, we apply this transformation on the whole matrix and extract the sublattice basis in the lower right block. This will generate a n minus k plus 1 dimensional submatrix that contains the last n minus k coefficients of the secret vector S. In this way, we encode the hints into the lattice basis. Compared with previous results, our work has advantages in various aspects. Unlike the DDGR framework in Crypto 2020, we are able to process multiple hints simultaneously. We're also significantly faster since we only rely on Gaussian elimination to perform the calculation. Compared with the MN method proposed in AsiaCrypt 2023, our method has a more direct and clearer proof of correctness. We also avoid rescaling the method, that is matrix as they do, since we focus on the dimension reduction on the left block alone. We compare the performance of these algorithms by experiments. And generally, we reduce the time cost of hint processing from hours to minutes. We explain this acceleration that first, we process multiple hints in one stroke. Second, instead of L3 reduction, we use simple reductions like Gaussian elimination. Third, our method avoids complex operations such as multiplying basis matrix with scaling factors. Now that we have constructed a ZSIS problem instance from hints, the next task is integrating it with the LWE instance. The theoretical basis of this task is that LWE and ZSIS share the same secret vector S. We'll now describe this process. The main technique is reusing the transformation matrix of hint processing. Note that in the previous discussion, we have got a transformation matrix U. We applied on the hint matrix. We remove the rows on the non-zero rows and the useful rows, or the 0 rows that we keep. We extend the hint matrix by appending LWE samples A and B, and also apply the transformation matrix. In other words, we process the A matrix in the same coefficients of processing the hints. Since we have known that the upper rows are independent from the required secret vector, we can just remove the first k rows of reduced A. This gives us a new LWE matrix with reduced dimension. In practice, we perform the transformation in these steps. After we obtain the U matrix by reduction of hints, we construct a matrix composed only from LWE matrix and append an identical block. Then we apply the transformation on this matrix and remove the first k rows, and finally obtain the new reduced matrix. Then we lift the LWE equation to integers by adding m rows of q vectors. In the lattice generated by this new basis, we can still ensure a short target vector which is derived from the original LWE secret. In this way, we get a new LWE lattice basis that integrates the hints. I'll continue to give a brief analysis of the quality of the new basis. First, naturally, our method reduces the dimension of LWE by k, since we remove k basis vectors in the process. Second, we suggest that the volume of the new basis is increased. This relies on the randomness of hints. A more detailed discussion and analysis of other kinds of hints can be seen in our paper. After that, we know the dimension and volume of new lattice. We use the BKZ estimator to predict the block size required to recover the shortest vector. We use this predicted block size to describe the hardness of the new LWE instance with hints. This figure illustrates our predicted block size and results our experiments, which roughly fit well. Based on the analysis above, we summarize our explanation about what happens in the too-many hints regime. Given k-perfect hints, we have suggested that the ZSIS can be constructed. It contains the target vector. In the average case, the secret vector V may not be significantly short in this ISIS lattice. We have to combine it with more LWE samples to construct an SVP instance. In the too-many hints case, however, the lattice already forms an USVP instance, and this allows us to extract V independently, directly from lattice. In other words, too-many hints is achieved when the hints provide enough information about S independently from LWE. This gives a new perspective on this special case and extends the observation of previous works. We provide experimental data for our implementation of combining hints with LWE and the whole attack. Our experiments are performed on a desktop computer. We mainly focus on perfect hints to give comparable results. The figures here present the BKZ block sizes and the time for experiments on crystal kyber with perfect hints. In our experiments, the number of hints k increases from 190 to 210. For every setting, we try integrating different numbers of LWE samples from 10 to 200. Generally, more LWE samples require a smaller block and slightly more time. We also compare our results with the MN method, and it shows that our method is significantly faster. Compared with their work, we only need fewer samples and hints to obtain similar performance. We also test our method on the too-many hints regime. We claim that this phenomenon is possible because a large amount of hints produce an ISIS instance that is already solvable by lattice-based reduction. Furthermore, given about half of the hints compared with LWE, we expect to recover the secret vector from L3 alone. We run experiments again on crystal kyber and first construct an SIS lattice, then run L3 or BKZ on it. In the gray area of too-many hints, we can recover the secret key with L3. In the white area, where fewer hints are provided, we still recover the secret, but with BKZ reduction. We call this phenomenon the broader sense of too-many hints regime. Given a large number of hints, we can recover the secret vector directly by L3. This means that we are in the too-many hints regime as described in the MN framework. Note that the MN needs about 2 hours for too many instances, or we use about 30 minutes. The main reason of the speed up is that the MN method runs L3 on n+1 matrix, while we run L3 on n minus k+1 matrix after extracting the sublattice. In summary, we developed a novel framework for LWE with hints. This framework is built on our theoretical analysis of LWE and with hints, which guides us in understanding how these hints provide information about the LWE secret key. Through our work, we offer an algorithm that converts LWE with hints to an SVP instance with provable correctness. Furthermore, our algorithm constructs the lattice faster than previous works by choosing Gaussian reduction as the main technique instead of L3 algorithm. Compared with previous results, our method processes all hints in one stroke and ensures theoretical correctness at the same time. This combines the advantages of both the existing algorithms. Experimental results demonstrate that our method is faster on cryptographic LWE instances. And this is our presentation. Thank you for listening. Thank you very much.